Thank you very much. So we have now Haider Sandman from University of East Anglia. He's going to talk about relaxation to equilibrium of 2D quantum vortex gases. Thank you, Haider.
Okay, thank you. So first of all, I'd like to begin by thanking the organizers for the opportunity to give this talk today. And I'm going to actually talk about work that was sort of initiated a few years ago with one of my PhD students, Davide Mastrini. But about 2 years ago, we made some important developments in terms of making a contact with experiments. And so I wanted to share these results with this community because given the theme of the meeting, I thought it would be of interest to people. So I'm going to be talking about modeling low-dimensional Bose gases, and I'm going to be focusing on regimes where sort of dispersive effects are important. So in contrast to perhaps the previous talk, which was focusing more on the role of dissipation on the vortex motion, we really want to be in a regime where the vortices are behaving as idealized point vortices as much as possible to realize some of these effects I'm going to talk about. And we're going to be focusing on 2D because, well, first of all, low-dimensional BECs can now be routinely realized, and in particular in 2D, there's a lot of interesting physics that can arise. For example, you're all familiar with the BKT phase transition specific to 2D systems. But I'm going to be interested more on non-equilibrium questions of vortex excitations and how this can play an important role in understanding the relaxation of a system to equilibrium. So that's the question I'm going to be interested in. And I will just sort of add by saying that when you're looking at 2D systems, they're rather special for a number of reasons. So I mean, first of all, vortex excitations can arise in 2D. They can arise in lower dimensions. But they are topologically predicted excitations, and they're nonlinear excitations. In some sense, they are sort of solitonic-like excitations. And so they are long-lived. They are quite robust, and it's not easy to get rid of them once you create them. So they are bound to play an important role in the relaxation dynamics. They have long-range interactions, so they can depend on the geometry of the system that you're in. And as we will see, they can satisfy some kind of adiabatic invariance, approximately conserved quantities. And so that can also have an important role in the long-time relaxation behavior. So the model I'm going to be focusing on predominantly is going to be just the Gross-Bitevsky equation. Actually, just for completeness, I'm including it here. So we've seen it several times already, but I'll just add by saying that since the wave function here needs to be interpreted as a 2D wave function, so the dependence on the third coordinate direction has been integrated out. And so the interaction parameter G is some kind of renormalized interaction that depends on the oscillator length scale AZ that's used to confine the VEC in the third direction. And of course, you can write this as a system of hydrodynamic equations through a Madelung transformation after introducing the hydrodynamic quantities as the density and the velocity or the current. And so you get a compressible fluid medium with a compressible continuity equation and the Bernoulli equation, where pressure is related to density only, so it's a barotropic system, with the caveat that you have this additional term, the quantum pressure term, that gives you the dispersive properties of the system. Now, whenever you want to understand the key basic property of a system, you need to start off by looking at the excitations that it can support. And so, of course, the most simple excitations one can think of is just excitation on top of a uniform background, which gives you this dispersion relation that's just the Bogly-Bose spectrum. So it has a phonon branch at low wave numbers and free particle excitations at high wave numbers. But you can also, of course, have solitons, or vortices, I should say, in 2D. And these vortices are depicted in these figures here by these density depletions, and they have an associated phase winding, which you can only get rid of by either sending the vortex to a boundary or by annihilating with a vortex opposite sign. So the associated flow field that's produced by these phase singularities has a 1/r dependence, and it has an associated circulation, has a typically comes, well, it's quantized, and typically we are interested in quantization of ±1, because these are the topologically stable excitations that we're going to be focusing on. In terms of the associated vorticity field, you should think of these as singularities in the vorticity field, so they have a delta function distribution of vorticity. Now, the important point to note when you start looking at vortices is that they obey essentially a Hamiltonian system in their own right to a leading order. And this Hamiltonian depends only on the interaction energy So it's a function of only the vortex positions. It has no term that looks like a kinetic energy term, so there's no momentum in some. And so the energy being dependent only on the positions tend to play a very important role on the relaxation dynamics, as we will see. So what we try to do is to invoke some ideas from classical fluids, so borrowing ideas that were originally developed by Lars Onsager, to describe this system of many vortices using statistical mechanical arguments. And since the state space is described completely by the positions of the vortices, then the phase space is equivalent to the configuration space of the system, meaning that the phase volume is just given by the integral of the vortex positions raised to the power n. And if you are dealing with a confined system, which is always the case in experiments, of course, then this phase space is bounded. It's not infinite as would be the case if you have a kinetic energy term, because momentum typically is unbounded. And so if I express the amount of phase space that's accessible below a certain energy, then I can write it in terms of this function phi, which I can re-express in terms of an integral with respect to the energy. And the Jacobian of the transformation that pops out is this quantity W, which is the wave function. And so phi itself will be a monotonic function that increases from some low value and eventually reaches a maximum because of the finite phase space. And so that means that when I look at the statistical weight, which is the derivative of this, you get a curve that has this characteristic feature. So on one side, it has a positive slope, and on the other side, it will have a negative slope. And if we recall that the statistical weight is related to the Boltzmann entropy in this way, so S equals KB times the natural log of W, and we relate that to thermodynamic properties. So namely, for example, temperature is just the derivative of the entropy with respect to energy. Then it tells you that on one side of that curve, you have positive temperature of the vortex gas. And then on the other side, you have negative temperature. And you're passing from positive to negative temperature through infinite temperature. In that sense, you can think of negative temperature states are hotter than positive temperature states for the vortex gas. Now, if you consider what's happening in the limit as you go far off to the left, then you're going to be dominated by vortex configurations that correspond to dipoles, so vortex-anti-vortex pairs. And far off to the right, you're going to be dominated by configurations that correspond to like-signed vortices clustering together. So in a coarse-grained picture, when you average out, you expect to have a non-trivial macroscopic flow field when you have vortex clusters. And so those are the two regimes that we will be considering. Now, to understand or to try to get a handle on what will be happening in the simulations, we developed this statistical mechanical framework using a mean field approach, where we introduce this mean field density for the vortices. So it just normalizes to 1 and is defined as the sum over the delta functions. And then from that, you can extend the definition of the entropy to a functional of this form. And likewise, the energy or the Hamiltonian of the vortices becomes the integral of the number density times this quantity phi, which is the stream function that can be related to the Green's function of the point vortices, which is just a logarithmic interaction that I presented earlier. And if you're dealing with geometries that have additional conserved quantities like angular momentum, so if you have rotational symmetry, then you also need to impose this constraint on M, which is the angular impulse that's related to angular momentum. So to determine the equilibrium states, you try to maximize the entropy subject to the constraints of the conserved quantities. So for energy, you have temperature. For angular momentum, you have frequency. And what pops out is a Boltzmann equation of this form. And so you see on the right-hand side, N is a function of the stream function phi that appears in the exponential there. So you have a nonlinear equation that determines the function phi. And that would be describing the equilibrium state of the vortices. Now, this would be the case for a single species gas. If you have vortices and anti-vortices in your system, you have to consider them as a two-species gas. And then you can extend the analysis by just so if you add this subscript A to distinguish between the species, but everything follows through as before. And now the entropy just generalizes to a sum over the individual species. And the total vorticity then can be recovered for the individual species by summing them together, and you still have this Boltzmann. Now, relating this to numerical simulations that were first done by the groups in Monash and University of Queensland, we came across this simulation that really interested us because it showed what happens when you start off with a random distribution of vortices in a disk geometry. And as the vortices evolve and annihilate, they form two large-scale structures, which is indicative of emergence of some kind of order from this chaotic initial condition. So it turns out that if we take our Boltzmann-Poisson equation, that's shown here now for the two species, and I find the gravest modes or the maximum entropy states of this, then you can find two solutions like that. And it turns out that the one on the left, so the dipole, is the maximum entropy as opposed to the quadrupole. And if I take the vortex positions, the instantaneous vortex positions in the simulation and just do a short time average, then we recover a dipolar flow field that looks like this. So that was the first indication that the theory seems to work for explaining these observations. Now, of course, over the years, the experimental capabilities have evolved. So there were initial experiments by the group of Zoran Hadzibabych, which were able to realize box traps. More recently, people now are able to use digital micromirror devices that we heard about already in two talks. And this is just illustrating some of the capability in the experiments of Queensland, where they were able to, for example, imprint these portraits of Satyendra Bose and Albert Einstein and Mona Lisa on their VEC. So just to demonstrate the capabilities. And they could do so while working with a highly oblate VEC, where you can study 2D vortex dynamics. So with that, we wanted to explore more general geometry. So we looked, for example, at the square geometry. And the first thing we do here when we look at the square geometry is that you remove the rotational symmetry that's present in your system, which means you no longer have angular momentum conservation. And because of that, what you find is that there's an additional type of maximum entropy solution for the vortex gas, which is the one shown on the right there. That is essentially a monopole distribution as opposed to a dipole distribution. Now, when you compare the relative entropies of these different configurations, so you find that there's in fact also a diagonal dipole, you find that the monopole in the square has the maximum entropy, the diagonal dipole has the next maximum, and then the dipole. And so we wanted to, the most stringent test, we wanted to see whether the simulations would coincide with these predictions. So we took a system of vortices that were initialized in a configuration to lie within the positive temperature regime. And then as the system evolves and vortices annihilate, the energy per vortex gradually increases, and also the system gradually migrates to the negative temperature regime. And then you expect to see clustering behavior. So with the point vortices, you actually have to mimic the vortex-anti-vortex annihilation by just pair removal. And when we did this, after some time, the system settled from the initial condition to this configuration that you're seeing there. And you can see that there is a dipolar configuration that's emerging. And if we do a short time average, you see a diagonal dipole. But if you wait longer, then the vortices reorganize themselves and they appear to mimic a monopole. So this was further evidence that the theory does seem to predict that the system likes to relax to these maximum entropy states of the vortices. We also tested this with the Gross-Petejevsky simulations in 2D. So here I did simulations with reflecting boundaries. So these are not periodic simulations, but reflecting boundaries to mimic the presence of hard walls. And again, you do the simulation, you see some clustering emerging. And so here we're just tracking the vortex positions in the GB simulations. And then you begin to see a diagonal dipole. And if we wait longer for the same simulation, fewer vortices left because some have annihilated, then you begin to see a monopole configuration. Okay. So these simulations gave us confidence that we are on the right track here, and provided you have a sufficiently large number of vortices and the dissipative effects are small, then you should be able to see this behavior, because dissipative effects, what they tend to do is to, if you have a dipole, instead of moving orthogonal to one another, then they prefer to sort of attract and they annihilate very quickly. And so the dissipative effects prevent you from remaining in this negative temperature states, and because they're bringing vortex dipoles close together, they push you back into the positive temperature regime, and so you do not see this. So a lot of these effects, you really need to have very clean systems. You need to have very low temperatures, control on the dissipation to begin to be able to see these hydrodynamic effects and the dispersion. Right, so looking ahead, we began sort of to take notice of the fact that there were a lot of interesting developments being made at the University of Queensland. So we already saw this figure here, where basically they were developing a capability to inject vortices with with very a lot of control. So for example, here you have two vortex clusters that were injected by just pushing a potential through the system, which leaves a phase field that leads to the formation of vortices. And they were able to produce around 10 vortices within each cluster. And the question then remained is, well, if you start from a far from equilibrium initial condition, will the system evolve and relax to an equilibrium state? Will the predictions of the theory work for these types of experiments? Now, it turns out that when you try to sort of make contact, of course, with the real world, there are always many challenges, unforeseen challenges that arise. Vortex anti-vortex annihilation plays an important role in driving you to negative temperature, but that also leads to additional complications in the dynamics. Vortices can also escape at the boundaries. Measuring things near the boundaries is not easy, and it also leads to additional complications. Detection of the circulation of vortices is not easy. So if you have positive and negative in the system, how do you distinguish between them? And so they came up with an alternative proposal, which is to look at a chiral vortex gas, where we go back to the disk geometry and we stir the system in such a way that we inject vortices of only one sign. And so you mitigate a lot of these problems, but there's still some interesting behavior that emerges because this actually system was first analyzed by Smith and O'Neill in the 1990s. And it turns out that there are at least 5 cases where you can even get analytical solutions in this problem. So if you go far off to positive temperature, so infinite positive temperature, you get a Rankine vortex. If you're at 0 temperature, you get a Gaussian vortex. If you're at 0 angular frequency, you have a Riccati vortex. But then as you keep increasing the energy, the distribution of the vorticity field wants to become more and more peaked. And as it wants to become more and more peaked, what happens is that it becomes also difficult to offset this against the conservation of angular momentum. And so in order to satisfy the conservation of energy and angular momentum that's imposed on the system, a bifurcation occurs, and the system all of a sudden prefers to develop an off-centered distribution of the vorticity field when you are in the negative temperature regime. And so this observation turns out to play an important role in testing some of the experiments against the field. So we are able to reconstruct the entire sort of phase diagram in terms of the entropy energy curve. So if you look at the top figure, the top of the figure there, so here you're in the negative temperature regime. At this point, there's this bifurcation, and the system develops another branch, which is asymmetric. And you can see this has a higher entropy than the symmetric branch. So you expect the system to prefer to be in this state. We also found from our Poisson-Boltzmann equation that there's another branch there which has 2 vortex clusters, and this was used to test other aspects of the theory against the experiments. Now, in all of these simulations I'm going to be presenting against and comparing with the experiments, you need to bear in mind that the Poisson-Boltzmann equation that you solve has 2 independent parameters only, the temperature and the angular frequency. And so we essentially have to test our theory with just 2 fitting parameters against the experiments. So the experiments were able to explore different parts of the phase space. So all of these dots here represent different sort of experimental, a set of experiments where many realizations were done to build good statistics. So you have an off-centered vortex, a forcing corresponding to 2 vortices initially, a near Riccati vortex, a Gaussian vortex, and so forth. And so we were able to explore different parts of the parameter space in experiments and try to compare with this theory. And so in the experiments, what they did is they used sort of like a paddle by sort of stirring it around. So they moved the potential through the condensate, and eventually they ramped it down. And as they ramped it down, they left a phase field that imprinted a set of vortices in the system. And so depending whether the paddle sort of extends all the way to the center or extends only sort of to some point off center, then you can imprint a cluster of vortices that are located centrally, or you can imprint vortices that are and they also used two paddles where they were able to also imprint two clusters of vortices, which after some time in the evolution, they saw that they prefer to merge into a single cluster here. So this is how the experiments were done. And then we moved on to make comparisons with the mean field simulations. And so the plots that I'm now showing you is, so this is the experimental distribution of the vorticity. This is the mean field predictions. And what you're seeing on the left here is the spatially integrated value of the density field with Y and integrated with respect to X. The symbols represent the experimental data that they measured. And of course, the solid curve is just the solutions of the Poisson-Boltzmann equation. And using just these two fitting parameters here, we're able to get this excellent match with the experiments. So this was for off-centered vortex. We tested it for the central vortex, so close to a Rankine vortex. This is what we saw. For the case with the double sweep, that eventually coalesces into a single vortex, you end up with a slightly different distribution. That's consistent with a different temperature and frequency of the vortex gas, and that's what we. And we explored the other two cases as well, and in all cases we saw a remarkably good agreement. So validating the right. Now, in all these cases, you might say, well, you're forcing so close to equilibrium that you're not really allowing the system to really evolve and relax the equilibrium. And so I'm going back to this case where the forcing was done such that you injected two clusters. And because we were able to identify a metastable branch of the mean field, the Poisson-Boltzmann equation, we were able to fit the distribution and quantify the entropy in this stage here. And after some time, it evolves to this point, and from the fits, we were able to extract the entropy from the mean field solutions for this regime. And when you compare the two entropies together, you find that there is indeed an entropy increase in the system. So as the vortices evolve, they do seem to relax from a far from equilibrium initial condition to an equilibrium distribution of the vorticity field, and with an associated increase in the entropy of the vortex. In terms of, then just to summarize the main results, I mean, we presented this mean field theory, which, as I said, goes back to work that we did a few years ago. And it explains many of the numerical simulations, both in terms of point vortices and Gross-Berezovsky equations. But it was remarkable that the agreement was strikingly so good with the experimental data from the group of Queensland. And so this, in a sense, provides the first quantitative agreement between theory and experiments for these types of problems. And so in terms of future work, we're looking at making stronger connections with 2D quantum turbulence, but perhaps also more interestingly to look at vortices and multi-component or spinor condensates. And so I'll just use this opportunity to advertise this work that was published, was a year or two ago now. And here, what you're seeing is a simulation of a two-component system where we have a phase mixing regime with weak intra-component interactions on this side, stronger interactions here. And so because one component begins to fill the vortices in the other component more and more as the interactions get stronger, you begin to see larger sort of vortex cores as indicated by sort of larger blobs here and compared to here. And this actually leads to very sort of non-trivial scaling behavior of the relaxation dynamics of the vortices. So what you're seeing on this figure is the time evolution of the intervortex separation as well as the spin correlation length. So here's the spin correlation length, here the intervortex separation. And you clearly see that there are two different regimes, and this other regime emerges that's specific to the effects brought about by the interactions between the two components. And so it'll be interesting to try and see how one can explore some of these ideas for these other types of vortices, where perhaps inertia effects become more important for these types of problems. Right, and I think I'll stop there.
Questions for Haider?
So thanks a lot, Haider. It was really interesting. I have two curiosities. The first is when you do the integral of a phase space at the beginning of the talk, you did not mention indistinguishability of vortices. Indistinguishability. Is there anything of this sense or not?
So in the statistics.
Bosonic, in the sense of bosonic, because every vortex is identical to another.
Yeah, yeah. I mean, I think, well, so it does, so when you do when you formulate it in terms of the microcanonical ensemble and you do the combinatorial analysis, I mean, I don't remember the details now, but I think it's built into the counting statistics that you built in. So I think the indistinguishability of vortices of one type are taken into account when you build it in.
When you take the distribution function is implicit, you say.
Yeah, but you make a distinction between whether it's positive or negative.
Of course.
Yeah, so it's built in.
And then another question. So in all your talk, you consider geometries with open boundaries. So a square or a circle.
Yeah.
So I'm wondering what happens if you use closed compact manifolds, like tori or spheres.
Yeah, so, okay, so I will say that, I mean, for quite some time, people were studying doubly periodic domains, which you can think of as like a torus.
Yeah.
And for some reason, they didn't observe any emergence of clustering behavior. And in fact, when I did some simulation periodic afterwards, because I was curious why they didn't observe it, I also didn't see it. And I think it seems to me, but it's something that's probably still an open question and maybe needs to be proven, that the interaction of the vortices with the sound is important, because when you have like a rigid boundaries, the momentum is zero. When you have periodic boundaries, there's sloshing that can occur as you exchange. And that seems to, I think, play an important role in preventing you seeing this. Because we saw these simulations from Guido Buffetta, where he saw emergence of clusters in 2D turbulence, which is similar in some sense to this, but that's purely incompressible. There is no compressible effects. And so I do wonder whether the compressibility is an important factor that, and the freedom provided by a torus that complicates matters.
And the image vortices don't play any role in your geometry?
Well, I mean, the point vortex model is simulated by using image vortices to account for the presence.
So you do include them?
Yes, yes, yes. No,
couldn't they be the reason of the separation?
I mean, image vortices are present whether you have periodic boundaries or whether you have the rigid boundaries, but it's just the nature of the images are a bit different to impose the different boundary conditions. So I think it's a bit more subtle, but it's an open question. Yeah, it's a good point.
Good. Thanks.
Yeah, thanks for the talk. Yeah, maybe it's totally off question, but when you have shown this, you start with an out of equilibrium state and then you kind of decay to some kind of dipole and then a monopole. Is there any connection or way to interpret that as pre-thermalization or not at all?
As pre-thermalization?
Yeah, the kind of the dipole state.
Yeah, I mean, I think the system is sort of trying to evolve to, I mean, true equilibrium in this system means there's no vortices. Everything annihilates, especially in the neutral vortex gas. Everything goes away. The point is that the communication between the vortices and the phonons is so weak that they are, that's why I said they are like a bit like they are adiabatic invariants. They are approximately conserved quantities. And within this subsystem, it's trying to get to equilibrium, and as it does, it moves through these different stages. So you go from a dipole, diagonal dipole, monopole, I think. So it is exploring this.
Heather, very nice talk. So I have the last question which Jacopo asked, is it a fine balance with dissipation and sound that you may get these clustering or clustered vortex states in periodic domains, or it's something totally different? That's one. Second question is, you were showing, these results with reflecting boundary condition. You showed a monopole state. So the negative vortices were aligning, or they were getting collected across, along the boundary, right?
Well, so you have vortices of one sign that seem to be on the edge, yes, and the vortices of the other sign seem to be in the middle. So that's the monopole.
Okay. So now with this picture, developing, is it possible to pass from this to a more continuum model, where I can describe, this vortices bunched together, and I can move on to models like HVBK?
Oh, HVBK.
I mean, this also goes. The question also goes to ML and maybe Matthew, I mean,
Yeah, I mean-
mostly in 2D, I mean, can I pass over from these, once the clustering starts happening, can I construct a field out of it and then have a field description, evolution of the field?
I mean, yeah, so if you're talking about HVBK models, and particularly in 3D, I mean, typically you don't have spontaneous emergence of clusters, so it has to be forced. But if it's in 2D, I mean, essentially, yeah, I mean, when you have clusters, you have large-scale flows, and that's the premise for the HVBK hierarchy. So the models that try to build sort of microscopic descriptions rather than microscopic models when individual vortices. So it is, you are in the same sort of regimes. And with regards to your first question, I mean, yeah, it's, as I said, it's an open question. I think the interaction between the vortices and phonons are important, but the details and why they seem to be preventing clustering in periodic geometries is still unclear.
All right, thank you. If you have more questions for Haider, he will be here, so you can ask him later. So thank you very much, Haider.